Okay, well, getting into the home stretch here. So I'm going to be talking about a project called the Metronome, which is a hard real-time garbage collector for Java. This is work we've done at Watson, Harry Cheng, Dave Grove, V.T. Rajan, and Martin Betcha, who's an intern with us this summer from Cambridge, UK. So, in the context of this workshop, to me, real-time systems are really kind of the final frontier of these virtual execution environments. Kind of one of the last holdouts of whole application areas that we can't touch, and that's really what the problem that we're trying to attack. And real-time systems are really growing in importance very rapidly. They're a very large and rapidly growing segment of the sort of installed base of processors. And one of my favorite quotes in this area is the CEO of BMW told told a gathering of employees that 80% of the innovation in their cars was going to be software. And to me, that's a really profound statement about the nature of software and real-time systems when a sheet metal company says this. But what's sort of happening is that programmers are getting left behind using methodologies that are very difficult to use. A lot of these systems are still programmed in assembler and C. Those systems are just much harder to program, and increasingly they're having to coexist with large sort of GUI-oriented, database-oriented, whatever systems that are often written in Java anyway. And so there's this kind of, they kind of have to go back and forth between these two worlds, and that creates, all sorts of organizational and management problems and training and all that kind of issue. So basically what you've got is a situation where you've got a lot of complexity, and you either have low reliability because you're using a bad programming methodology, or you've got a very high validation cost to make sure that stuff that you've written in assembler really is correct. So just to sort of put some things in context here, I'm really going to be talking a little bit more broadly about time-sensitive applications. That includes sort of traditional hard real-time, soft real-time things like games and media, and also sort of operating system components like device drivers and fold handlers, which are really, in some sense, real-time subsystems. The work that I'm going to be presenting is explicitly designed only to run on a uniprocessor. Use of multiprocessors in real-time systems is still pretty rare. Usually these systems are running on smaller devices. And although this complicates things in the sense that we have to very carefully interleave the collector and the mutator, it does simplify things significantly because we don't have to deal with a non-sequentially consistent memory model, and we don't have to deal with true concurrent updates, and so we're able to gain some very important efficiencies in things like software readback and stuff like that. So the goal when we started this project was to make garbage collection. Yeah?
Even as a single process, it could still be multi-threaded, and the processes are not frequently by themselves.
The
irony is that's what
yeah. Yeah, I mean, certainly we're, the applications will be multi-threaded. Yeah. Okay, so we really wanted to make the use of garbage collected systems feasible for constructing hard real-time programs. And as important is for this really to have a very simple interface to the user If you've ever looked in any kind of detail at RTSJ, it quote unquote gives you real-time Java, but the interface that you have to deal with and the impact on libraries and how you can use all of the software is really large. And so we're trying to really keep that a very simple Java programming model. So within that framework, we want something that's comparable in both throughput and space consumption to a good stop-the-world collector. And sort of our motivating scientific goal was to break the millisecond barrier to basically get to the point where we could have sub-millisecond response time in a garbage collected system while still providing smooth CPU utilization. Okay, so that's what we wanted to do. Where are we? So we currently have a system with maximum pauses just under 4 milliseconds. We can guarantee that with a utilization during garbage collection of 50% with a jitter of about 1 or 2%. And we have a memory requirement that's almost always under 2 times the maximum live data of the application, which is better than any semi-space collector will do, and better than, as good or better than most production collectors. Okay, so I'm really only going to be giving you kind of a sketch of the system today. But I'm really going to, I'm going to spend a lot of time talking about, really the most important issue, which is controlling the time aspect of this, which is the scheduling. So, probably a lot of you are familiar with Baker's 1978 paper, which is sort of the first one on real-time garbage collection. And he put forth this definition that pretty much, almost everyone has followed since then. He said, a real-time list processing system is one in which the time required by elementary list processing operations is bounded by a small constant. And this is sort of a very appealing definition, and it's sort of so, obviously true that people haven't really questioned it much. But it doesn't really work. So there's a bunch of things going on. So here I've shown the execution over time of a task. Okay, and these little green things are these elementary list processing operations. In 1978, Lisp was the only garbage collected language, so apologies to small talk. You will live. Okay, so we're doing these, operations. These might be allocations. These might be barrier writes or barrier reads, whatever. And at this point, the real-time task finishes, and over here is the deadline. So we're happy we finished before our deadline. So the first thing to notice here is that these little green things are not evenly distributed, right? Sometimes you do a lot of allocations. Sometimes you do a little. Sometimes you do a lot of writes. Sometimes you do a little. The next issue is that this small constant generally isn't so small. I think when someone says small constant, we intuitively think, 3. But small constant, right? So if you take a read, which is a load index, and you turn it into a load compare. Oops, I'm in barrier mode. Branch, go into a loop and copy a bunch of objects, which itself is a loop. Small constant is 20, 50, 200. And then the other thing is that sometimes these operations, sometimes you take the fast path, sometimes you don't. So the distribution of when these things get slowed down is also uneven. So you might have a situation where, say you've just started collection before here, so almost all of these things are sort of in a fault. And there's sort of an analogy when you start